Hello and welcome to this lecture on fundamental of electric drives. In the last lecture, we were just discussing about the continuous current operation of a single phase full controlled converter. We will continue with that. Now, we have a single phase full controlled converter. This is the converter here, and the load in this case is a armature of the DC motor. This is the armature of DC motor separately excited, and the current through the load through the armature is continuous. This is how the current flows in the armature. This is the plot of current and voltage and current against omega t, a time or angle, omega t is the angle. Now, we have to find out the average armature voltage, which is straightforward here because we have a continuous current. So, if you want to find out the average armature voltage can be evaluated by integrating for 1/2 cycle of the input voltage waveform, that is 1 by pi from alpha to pi plus alpha. This is V m sin omega t d omega t. Now, that is equal to 1 by pi into V m minus cos omega t. This is pi plus alpha to pi, this alpha to pi plus alpha, this is alpha here. So, what we get here is 2 V m by pi into cos alpha. So, this is the average output voltage of the bridge, which is the armature voltage of the DC motor. Now, if we apply this armature voltage, which is 2 V m by pi cos alpha, what will be the torque speed characteristic? So, if we apply this to the armature, so this is 2 V m by pi into cos alpha is equal to the resistance drop R A I A plus the back EMF E, or from this we can get the value of speed. Speed is equal to 2 V m by pi cos alpha. This is divided by k phi minus R A T by k phi square. So, this is the speed torque characteristic of a separately excited DC motor when fed from continuous, when the condition is continuous, and we also evaluated the speed torque characteristic for discontinuous current operation. So, this is the speed torque characteristic for discontinuous armature current. So, these two are key equation which will help us plot the speed torque characteristic of a separately excited DC motor when fed from a single phase full control converter. Now, let us see this characteristic here. Now, when we go on varying alpha here, the no load speed will change. This will change the no load speed. However, the slope of the characteristic, this is the slope of the characteristic, will almost be the same, because the armature resistance is not changed. So, if we plot this torque speed characteristic, taking the speed in the y axis and torque in the x axis, we plot here for various values of alpha, alpha equal to 0 degree, alpha equal to 30 degree, alpha equal to 60 degree, and then we can also plot alpha 90 degree. Now, when alpha is 90, we can see that the no load speed is 0 if the current is continuous. So, at lower value of torque, there is a tendency of discontinuous current operation. So, torque the current become discontinuous at lower value of the load, lower value of the torque. Now, here in this case, as the torque becomes smaller and smaller, towards the lower value of the torque, the current will be discontinuous. So, we will have operations shifted to some other region. So, this is governed by the previous equation, and this is the no load speed for discontinuous operation. So, this is for alpha equal to 30 degree, alpha equal to 60 degree, and alpha equal to 90 degree. And we have a boundary condition. This is the boundary. So, this is continuous current operation, and this region is discontinuous current operation. And what about the no load speed? The no load speed for discontinuous current operation is given by Vm by k phi. This is the no load speed. However, if we extend this continuous current operation, if we extend this, suppose we assume that current will remain perfectly continuous. So, this will toss the y axis at a value which is 2 Vm by pi into k phi. So, the no load speed under discontinuous current operation is Vm by k phi, because the back EMF under no load condition is equal to Vm, and that is why the no load speed for the discontinuous current operation is Vm by k phi. So, we can mention here that back EMF for no load condition for alpha from 0 to 90 degree is equal to the peak of the supply voltage. When the back EMF is the peak of the supply voltage, current is equal to 0, and that is why the torque is equal to 0. So, this corresponds to the situation when the back EMF is the peak of the supply voltage. So, when the back EMF is peak of the supply voltage, so which means Vm is equal to E is equal to k phi omega m naught, that is the no load speed. So, what is the no load speed here? That is equal to Vm by k phi. Now, what we see here, that for discontinuous current operation the load is less. So, for a given alpha, if the load is reduced, the motor enters into discontinuous current operation, and for discontinuous current operation the equation is this equation. So, this equation is for discontinuous current operation. Discontinuous current operation. So, and when the load is higher, the motor operates in continuous current operation. So, this is continuous current operation. Okay. So, this equation is for discontinuous current operation, which relates the speed with the torque, and this equation is for continuous operation, which relates the speed with the torque. And what we see here, that in continuous current operation the characteristic is a straight line almost parallel to each other. When we draw this for various values of alpha, they are almost parallel to each other, and the speed regulation is good, but when the current is discontinuous, the characteristic becomes like this, and here the speed falls quite quickly. The speed regulation is poor for discontinuous current operation. The speed falls very quickly, and there is a boundary between continuous current operation and discontinuous current operation, and the boundary is decided by omega m is equal to omega c, the critical speed. When the speed is less than the critical speed, it is continuous current operation. When the speed is more than the critical speed, the operation becomes discontinuous. Now, when we still increase the value of alpha, what happens? Suppose we make alpha 120 degree. Okay. So, alpha is 120. So, this enters into the braking region, and then alpha 150 and so on. So, we have certain Euler speed here, and this is the braking region. So, we have the motoring and we have the braking. The motoring happens in quadrant 1 and the braking happens in quadrant 4. Now, let us see how do we go for braking with a full control converter. Now, let us see that we have a full control converter, which is shown by a block here, and this is supplying motor load, resistance, inductance and back EMF. Now, this is VA and this is the back EMF, which is E, RA, LA, and the motor is connected in the following fashion. This is the equivalent circuit of the motor. The actual motor has a back EMF, which is here, and the field is separately excited. This is a single phase full control bridge. So, this is motoring, and the motoring happens in first quadrant. And for motoring, the speed is in one direction. So, the speed is let us say positive, the torque is positive, and what is the value of alpha? Alpha for motoring is from 0 to 90 degree. Now, this current here, current is only in one direction, current can only flow in one direction. So, for motoring, this flows into the motor and the operation is in first quadrant. Now, we go for braking. Now, when we go for braking we have the same converter here, fed from AC supply. And what about the motor? The motor back EMF has reversed. So, unless the back EMF reverses, we cannot have braking operation here. So, this is the resistance and the inductance, and how does the back EMF reverses? The back EMF can reverse provided we have a negative speed. So, speed is negative here. So, if this is omega m, this speed is opposite of that. So, the speed is negative and the back EMF has reversed with this minus and this plus. So, this minus and this plus here, and the current is always into the motor, that is I A, because we have a unidirectional converter. Thyristor can only take current in one direction. So, here this is braking because the back EMF has reversed. So, in other words, the motor is supplying the energy, the back EMF is giving this energy. So, this happens in fourth quadrant. So, this happens in fourth quadrant. So, what is the value of alpha here? Alpha is operated beyond 90 degree. So, this is 90 to 180 degree, and here the speed is negative. So, omega m is positive here for motoring, omega m is negative here, that is for braking. Now, this braking is a regenerative braking, because the kinetic energy of the motor is fed back to the supply. The converter, the single phase converter is operating with alpha higher than 90 degree. So, the output voltage here V A in this case has reversed. So, the output voltage has reversed here. So, if we see the converter voltage, that is V A, the power is negative, which means the power flow is basically from the load to the supply. But in case of motoring, the power flow is positive, which means the power flows from the supply to the motor, to the load. Here the power flow is negative. So, that is why we call this to be regenerative braking, and this happens in fourth quadrant. So, if we have this quadrant operation, we have the speed here and we have the torque here. The quadrant 1 is for motoring and quadrant 4 is for the braking. So, this is forward motoring, and for this alpha is from 0 to 90 degree, and the quadrant 4 is for regenerative braking, and we call this to be reverse regenerative braking. And for this alpha is greater than 90, is less than 180 degree. So, we can only go for reverse regenerative braking provided we have the negative speed in this case, and that is possible for overhauling load like the active load like lift etc. Those loads can be braked regeneratively. Now, this is what is about a full controlled converter. Now, let us see actually the operation of a half controlled converter. Now, we will be discussing about half controlled converter fed separately excited DC motor. And this is a single phase, half control converter fed separately excited DC motor. So, what is the converter structure? The converter in this case has got 2 SCRs and 2 diodes, and it supplies the armature of a DC motor, the resistance, the inductance and the back EMF, and input supply is AC supply. Vs. The output is the current here, and this is the output voltage. Now, as we have seen in case of a full control converter, a half control converter can also operate in 2 different modes, a continuous current mode and a discontinuous current mode. We will take up these 2 modes separately. Let us try to take the discontinuous current mode first. Discontinuous current mode. So, if we see this operation of this converter, we have the input supply which is a sine wave, this is the negative of that supply, and we have a back EMF which is E, and we trigger at an angle alpha here, this is pi and this is pi plus alpha. Now, if we trigger at an angle alpha, the current starts from 0 and will at pi, when the voltage will try to become negative, the diodes will be forward biased. So, in this case what we have a freewheeling path. The freewheeling path is through these 2 diodes. So, the voltage will not become negative. So, the output voltage will be of this sort, and at this instant the voltage will remain at 0. voltage will remain at 0 and the current will come down to 0 exponentially. So, this is the nature of the current. So, this is I A and this voltage is V A. So, this is how the voltage change, this is V A and then from this the voltage will be 0 and when the current is equal to 0, this angle is called the extinction angle, that is beta, as before. And after that the voltage will become the back EMF. So, at this instant the voltage will build up and will become the back EMF of the motor. So, the output voltage will look like this. So, this is the nature, and if it is periodic, it will somewhat be like this. So, this is output voltage, and if the operation is periodic, the voltage will be of this nature. Now, we can divide the discontinuous current operation into various modes. The first one is called the duty interval. When omega t is greater than or equal to alpha and less than equal to pi, we call this to be the duty interval. Duty interval. It means from alpha to pi, the supply voltage is available at the output. So, we can say that we have a RLE circuit, we have V A is equal to R A I A plus L A d I A by d t plus E, and we have the duty interval here, and that is equal to V m sin omega t or V s. And what is V s? V s is V m sin omega t, it is sine voltage. So, that is equal to V m sin omega t. So, as before, this equation will have a steady state component and a transient component. We can write down the equation of this. I A is equal to V m by z into sine of omega t minus theta minus, as before, we can write down E by R A plus E by R A minus V m by z sin alpha minus theta exponential minus omega t minus alpha into cot theta. Here what is z here? Z is the impedance, which is equal to R A square plus omega L A square, the impedance of the armature resistance and the armature reactance, and theta is tan inverse of omega L A by R A. Now, this equation is the equation of the current for the duty interval. Now, again we have a freewheeling interval. Now, when omega t equal to pi, this current I A reaches a value, that is I A pi. So, at omega t equal to pi, I A reaches a value I A pi. So, this value is I A pi. When it reaches the value omega t equal to pi, this is I A pi. So, we can substitute the value of omega t and find out what is I A pi. So, I A pi is equal to V m by z sin pi minus theta minus E by R A plus E by R A minus V m by z into sin alpha minus theta exponential minus pi minus alpha cot theta. So, this is I A pi, and then after that, after the duty interval, there will be freewheeling interval. The voltage cannot be negative, the diode will freewheel the load current. So, these two diodes will be forward biased, because this voltage will always be positive. So, when the voltage will be close to 0 or little bit negative. So, these two diodes will be forward biased, and the load current will be freewheeled through the diode, and that is called the freewheeling interval. And for freewheeling interval, the current is 0. This is the freewheeling interval. So, for freewheeling, the current is exponentially decaying, the voltage is actually 0 here. So, we have the freewheeling interval, and this is for omega t greater than pi less than beta. And for freewheeling interval, what is V A? V A is ideally 0, because the output is being freewheeled, output is short circuited by the diode, and if the diodes are ideal, the output voltage, that is V A, is equal to 0. So, that is equal to R A I A plus L A d I A by d t plus E. Now, this is again a first order differential equation, and we can solve this equation in a very similar way, steady state and transient. So, what is this solution? I A is equal to, the steady state is minus E by R A, the transient part is like some constant, that is A exponential minus omega t cot theta. So, this is the solution of the differential equation, and we can substitute the initial value at omega t equal to pi, I A is equal to I A pi. So, I A pi is equal to minus E by R A plus A exponential minus pi cot theta. So, we can evaluate what is the value of A here. So, value of A is I A pi plus E by R A exponential pi cot theta. So, we can substitute this value in the previous equation. If it is equation number 1, let us say, we call equation number 1, this is equation 2, and this we call equation 3, let us say, this is equation 4. So, we can substitute the value of A in equation 4 here, equation 3 in this case. So, what is I A here? I A is equal to minus E by R A plus I A pi plus E by R A exponential minus omega t minus pi into cot theta. So, this is the equation of the current, and this current is valid for the freewheeling interval. Now, at the end of the freewheeling interval, this current is equal to 0. So, we can substitute that again to find out the value of beta. So, at omega t is equal to beta. So, beta is the extinction angle, I A is equal to 0. So, we can say that 0 is equal to minus E by R A plus I A pi plus E by R A exponential minus beta minus pi cot theta. So, this equation again involves the value of beta. So, beta can be evaluated from this equation number, let us say 6, iteratively. So, beta can be evaluated from equation 6 iteratively as before. Now, if we want to plot the, or if you want to find out the average value of the voltage under discontinuous current operation, we have to do an integration. So, the integration can be performed like this. So, B A is the average value of the voltage over one half cycle. So, what we have to do is that we have to integrate from alpha to pi, and this is V m sin omega t d omega t, and then we have to integrate from beta to pi plus alpha, that is E, the back EMF. Now, if we see the voltage waveforms here, the voltage from alpha to pi is V A, and then the voltage is 0, the voltage is again some finite value, that is E from beta to pi plus alpha. So, this is what we have obtained here, and if we solve this equation, we will get the average value of the output voltage for discontinuous current operation for a half controlled bridge converter. So, and from this also we can find out the torque speed characteristic for a half controlled bridge converter fed separately excited DC motor, and the analysis of the torque speed characteristic will be performed in the next lecture.